Good day, everyone. Our topic for today is about sequence. Actually, a sequence can be defined as a set or as a function. But here, we will define a sequence as a function. But first, we note this notation. We have this notation of function from D to R. This is the real valued function. Whereas if we have this notation from D to R star, we call this function as extended real valued function. So let's define now a sequence in R. It is a real valued function defined on N. Now here, take note the domain is the natural number, the set of natural numbers. So let's have here this illustration. So from N to R, this is a function from N to R. So the image of 1 is f of 1, and we let that 1 as x of 1. So the image of n is f sub n, which is equal to x sub n, and so. For the notation of sequence, we have this one. So this is the notation of sequence, where x sub i's are the images of the element of the set of the natural number under the function or sequence f, and x sub j's is the jth term of the sequence. So this is the first term, second term, and this is the nth term of the sequence. Now let's define the limit of a sequence. Okay, we let a real number L. So L is the limit of the sequence x sub n if for every epsilon greater than 0 there exists a natural number n such that this will hold. For all small n, natural number small n greater than or equal to n. Now let me illustrate this. The existence of big natural number n such that with this condition for all small n greater than or equal to n. So let me have this one. When we say, okay, let's have this first. There exists big N or a natural number n such that this holds for all n greater than or equal to big N. So when you have this one, it means that we have negative epsilon x of n minus L. Then this is L minus epsilon L plus epsilon. Okay, so it means here that x sub n, small n, is in the open interval L minus epsilon to L plus epsilon. Okay, so let us try to have this example. Say for example, we have here our sequence x sub 1, we have x sub 2, x sub 3. This is just an example now. Say n sub 1, x sub n sub 2, x sub n sub 3, say x sub n 4, then we have x sub small n 1, x sub n 2, x sub n 3, and so on. So if we are to illustrate that one using the real number line, So if this is our limit of the sequence L, we have here our open interval L minus epsilon, L plus epsilon. Then states there that there exists n, a natural number big N. So say for example, ano na siya, such that this open interval here sees the terms of the sequence x sub n, small n greater than or equal to n. So what's inside here are all the sequence with n greater than or equal to n. So kani siya tanan. And then kani siya, the rest of this will be outside the open interval. Say for example, let's have here, this x sub 1 is here, say x sub 2 is here, x sub 3, so we have here x sub big N sub 1, say we have x sub big N sub 2, say we have here x sub big N sub 3, so now there is x sub big N sub 4. So, kani siya tanan are inside this open interval. Say we have x sub small n sub 1, here say x sub small sub n sub 2, x sub n small n sub 4, say here x sub small n sub 3, and so on and so on. So we have here, as you can see, there are infinitely many elements or terms in the sequence within this interval. Okay, x sub n sub 3 and so on. So if we have here x sub 3, it would be x sub n sub 5 here, 6, and so on. So they tend to approach the number L, which is what we call the limit of the sequence. And we have a restatement of this. L is the limit of the sequence if and only if, for all epsilon greater than 0, we have here our open interval as what I have illustrated a while ago. So we have here the open interval, this one, the open interval. Ito. This is the open interval L, L minus epsilon, and this is L plus epsilon. So it contains now infinitely many terms of x sub n, is what I have said a while ago. And of course, outside of that, this interval here is this one outside of the open interval, and this interval here is still outside of this open interval. They contain finite number of terms of the sequence x sub n. So kumbaga, most of the terms of infinite terms of the sequence are found here. They tend to approach what we call the limit L of the sequence. So in symbol, we have here x sub n approaches to L as n approaches to positive infinity, as this approaches to positive infinity. Or we can say that the limit of x sub n as n approaches to positive infinity is equal to this, which is L. So let's now have the cluster point of the sequence. So for the cluster point of the sequence, we have here a real number L is a cluster point of the sequence if given a natural number big N and given epsilon greater than 0, there exists n greater than or equal to big N such that this will hold. Now, what's the difference between the limit of a sequence and the cluster point of a sequence? Okay, let's have the restatement of this definition. So L is a cluster point of the sequence if and only if, for all epsilon greater than 0, L minus epsilon, this open interval L here, contains infinitely many terms of x and n. So let us consider this. Okay, this is for a cluster point. We have given n, natural number n, and the epsilon greater than 0. So there exists a small natural number n such that this will hold. So of course we knew already this one, that this means the sequence x sub n is in the open interval. The terms of the sequence are in the open interval where L is the cluster point. So what's the difference between the limit of a sequence and the cluster point? Now take note for the limit. Big N there is the existence of big N, such that this will hold for all n greater than or equal to big N. But here in the cluster point, given the big N, and then there exists rather n greater than or equal to n. This n here could exist once, twice, or many times. So existence lang man siya, such that this will hold. So in this case, if from our restatement of the definition, there are infinitely many terms of the sequence inside the open interval, but wa siya nag-ingon nga outside finite, right? Kung sa limit, outside of this open interval are finitely many terms of the sequence. But here, because we base on the existence of n, given n, it could be pila ka buok ang mo exist nga n, which is greater than or equal to n. So, therefore, we could have, say for example, na napilain mo may exist, we could have another L. So, kaya man siya giingon nga finite dito. So, it could be infinite diha as long as infinite ang inside the open interval. So, let's name this L1, 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 here L2, L2 minus epsilon, L2 plus epsilon. So, as long as there are finite number of x sub n here, where n is greater than or equal to big N, the same thing here. So, it could be one or more. We could have one or more cluster points in a sequence. Whereas, sa limit, there is only one limit, and it is unique. Now, let's have this remark here. If L is the limit of the sequence, then L is, of course, a cluster point of the sequence. In fact, L is the unique cluster point of the sequence. Now, a cluster point of the sequence is not necessarily the limit of the sequence, as can be seen in this example. So, let us try to consider the sequence except the sequence negative 1 to n. So, we have these terms here, negative 1, 1, negative 1, 1, and so on. So, we let epsilon equals 1/2. So, as you can see, we do have two cluster points, negative 1 and 1. So, this is the open interval negative 1 minus 1/2, negative 1 plus 1/2, and so on. Here, it contains infinitely many terms of negative 1, and here, it contains infinitely many terms of 1. And that's it.